Yeah, well, we really appreciate your being here today. And, we've been having an ongoing conversation this summer around a series of presentations in this space, all designed to help us kind of build a robust conceptual foundation for understanding what we're calling the energy poverty nexus. And so I think this is going to add to that conversation in highly productive ways.
Okay, perfect. Excellent. And thanks, Elena. So a bit about our team. The focus and the mission of the team is on creating technical and business solutions that facilitate the global transition to a resilient low carbon economy. And we personify that in a variety of ways, domestically, internationally, small scale, large scale, technical, business, policy, etc. But that kind of mission statement is quite important to us because although we're principally a group of engineers, we realize that the creation of science is well undershoots or is insufficient to make substantive change in the world. We need to understand the dynamics of various user groups, how to create those solutions in a financeable value that is tangible, and to provide the training and support to see that happen. We realize also that it is a transition of getting to a future that is a low carbon economy. And while we also are focused and strive for being net zero or even negative carbon, we realize that as a society, that's going to be a multi-decade approach. And so while there's, individual pieces might be carbon sinks or net zero carbon, society as a whole has a long ways to go to transition to even being low carbon. And that transition will be unfolding for 3, 4, 5 decades, and that's where our focus is. We do basic and applied research. We have a 1-acre microgrid test bed at the Polytechnic campus where we test commercial technology, build and construct our own, and then we do field deploy that in refugee camps, international markets, domestically at campuses, military installations, urban centers, and a variety of software developers that we work with to put some of our algorithms behind too. And we're very happy to be involved in workforce development as well, which will be part of our conversation today. Next slide, Elena. So a little bit about our approach is we do take that scientific and business background. And so when we think about problem curation, typically in the academic sector sphere, it's focused on what is the gap in the literature. Whereas my work and the other folks in the team that have a background in the private sector, the focus is instead on user surveys, understanding your clients and developing products that meet needs that are stated or unstated. And so when we think about innovation, we need to bridge or bring together both what is a scientific gap, but then what do people want to create something that provides fundamental and transformative change in either creating a new product, a process, or people, realizing that science and technology is not the only part of the goal, and it might not even be a part of the end solution being delivered. We might find that we actually have the best solar panels or the batteries or whatever it is, but we don't have a way to warranty, service, or deliver those out to the end user. Or we might have a great opportunity, but we find out the policy doesn't accommodate that or could be changed to help propel the renewable energy future forward. And so our solutions are generally multifaceted across that bottom approach. Next slide, please. And so Elena and I are going to talk about 2 areas of work that are more germane or pertain to the folks on the horn with us today, is in off-grid solutions, so international development aspects, and then workforce development. And so with that, I'll be turning it over to Elena to talk more about our earlier, my last one, sorry, Elena, is we realize that as you take a look at rural electrification or even areas that are urban and have power, such as in Haiti, is that we are afforded in the United States with a relatively low cost of power with respect to most locations in the world. And so as you think there on the left with that higher price of power being just under 3 times the price in Haiti as it is in the United States, and it's also poor quality power. And so the World Bank and ESMAP, so ESMAP is a division of the World Bank, is the best rating that they have for power access is that you have a maximum of 3 disruptions per week and any total duration is underneath 2 hours. And you can imagine talking to anyone on the call here and saying, yeah, I don't mind my power getting cut 3 times a week. And, if the power is out from 1 to 3, p.m. on a Wednesday afternoon, no problem in Arizona. And so we think that the regulation, the promoters, and the sponsors are not pushing for a high enough quality or level of standard for what the industrialized world has become commonplace for the quality of power. But even as South Africa and other countries have installed more renewables or hydroelectric power, that doesn't necessarily mean those still meet all of their needs. And since there's massive droughts in areas of the world, here and in South Africa, just because we've installed those systems doesn't mean they're actually now able to maintain pace. And as I was working in Southern African developing countries 10 to 12 years ago and experiencing lots of rolling blackouts, those are coming back today due to poor planning and poor operations. And so it's the price of power is high, the standards are insufficient, and our emphasis is how do we drive technology change, policy change, and business models to create something that is lower cost, more reliable, and has a lower footprint on the global carbon. So I think, Elena, that's my last transition. Over to you.
Yes. All right. So we'll be going over 3 project areas, and I'm going to start us off with technology design for mini-grid rural electrification. So the challenge we're trying to address is mini-grid site analyses processes include costly data collection and limited technical feasibility assessments. So these are the standard processes that are going on. And what this means is when the World Bank or a government agency says, for instance, this area of Nigeria, we want to put 50 mini-grid sites in there. Let's identify what locations are the best and what are the financial metrics associated with those projects. Well, right now that process is very costly and time-consuming, and simultaneously includes limited technical assessments of what the infrastructure expectation and power system expectations are of those actual mini-grid sites. So our solution that we're proposing and the tool that we're developing right now is to improve the evaluation efficiency by over 90% through rapid mapping and in-depth techno-economic analyses. What we're doing is we're taking remote GIS data, moving it and doing power system analyses to finally come out with more accurate financial specifications for the project. And I'll go into those steps. So the underlying motivation here, which I think most of us are aware of, is that thousands of remote villages or islands do not have electricity right now, and mini-grids can provide that last mile electrification. However, right now, the planning processes are being hampered by these slow initial assessments. So this breaks down our assessment methodology, and I'm actually going to go into the specific steps and talk about how they compare to standard methods. So first, there's the primary data collection and feature identification. This would be where in typical assessments, there would be door-to-door surveying of households, of businesses, and so on to get willingness to pay and other load estimation data. However, this is a very costly and time-consuming process, and there's actually literature to back up that although these surveys are good indicators for what the electrification demand expectations are going to be, they are not accurate enough to provide concrete estimates that would then advise technical solutions. So what we are suggesting is to use remote data, remote GIS data, to collect where load centers are, so where households and then where streets and so on are, and that's with a partnership with youth mappers, which I'll go into later. At this step, we also get our resource and asset availability for generation sources, collect the energy regulation and policy that's appropriate to that specific location, and then we do that load estimation. However, our load estimation methodology is much more based on proxy, so comparing what the electricity demand is in a similar sized village, since we're having dozens of mini grids are already popping up, for instance, across Africa that we can compare to. The next step is then to translate this GIS data that I spoke of into Zindy and OpenDSS, which is where we do the power system analyses. Step 3 is then preliminary systems design. So this is where, in a standard method, you would do the technical assessment and stop. This would be high level, choosing generation assets that are appropriate to your load estimations, and typically making lump sum estimations of what other costs of the system would be. So that's like poles, conductors, controllers, and so on. In our processes, this is, however, a first step for us to go into the power engineering assessment. So at step 3, we look at, again, what are those initial asset sizing, but we also take a look at clustering, so bringing those loads together, which is making it easier for us to do the power engineering assessment, identifying the size and boundaries of the mini grid, and then also investigating initial generation asset placement. So at 4, we actually do that power engineering assessment. This is where we're identifying network designs, low voltage versus medium voltage, and using Zindy to actually do that power flow assessment. So for instance, what could come out of the power engineering assessment is that the previous assumption was that it was a low voltage network. However, through our power engineering assessment, we find that a medium voltage network is required in addition. Now, the extra costs associated with conductors, transformers, and so on are significant in adding to the overall project costs. Therefore, we're able to have more accurate financial indicators for what the project costs are finally going to be. So then in step 5, we do that business model evaluation that I just explained, looking at cost recovery models, final cash flow model, cost estimation, and so on. And then finally, we take the network that we have preliminarily designed in Zindy and OpenDSS and bring it back into GIS software for planning, and to later be able to inform mini-grid developers. So we've worked on 2 projects so far to develop steps within this methodology. The first one was with PowerGen. So PowerGen was funded by USAID to identify 70 off-grid communities in Niger. And for 10 of those, we looked at supporting them in doing a specifically in-depth technical assessment. And through this project, we were able to develop step 2 of the process, which is the data translation process. This can be a very time-intensive process, that's what you can see on the right-hand side, getting information from QGIS actually into the power flow software in Zindy. So we developed that and we're able to reduce time in this step by 90%. The next project that we're working on, and this is actually ongoing right now, is also with PowerGen. So this time PowerGen is funded by USTDA to identify 45 off-grid communities in Sierra Leone. 40 of those are village settlements and 5 of those are with commercial and industrial presence. So within this project, we've been focusing more on step 1. So how do we get the initial, especially GIS data, and make that seamless flow then into our power engineering assessment? So to identify the GIS typology, we've partnered with Youth Mappers. Youth Mappers is a really great organization. They're student-led and work internationally, have over 200 chapters in 50 countries. So actually they have a chapter in Sierra Leone that is helping us map specific communities. And it's been really great to work with them in identifying how can we more quickly gain these remote data and more efficiently. So the overall benefits of our rapid mapping tool, one is decreasing planning time at this initial stages of the project. Then 2 would be providing an optimized microgrid distribution network topology and asset placement strategy. So by doing that extra technical assessment, we're able to come out with more accurate technical specifications for what that mini grid is expected to look like. And then finally, of course, we're able to obtain more realistic financial metrics such as levelized cost of energy, total capital costs, and payback period. And that's, of course, important to the funding and donor agencies looking to support mini grid rural electrification, so they know what the expectations are for these tens of millions of dollars that are being put towards these initiatives. So this rapid mapping tool is not only good for off-grid communities, it can also be applied to, for instance, refugee settlements in certain circumstances, and then, of course, islands as well, which require mini grids. So our scaling plan from here, we are funded under an Office of Naval Research Neptune II grant to support the development of the data translation process, more specifically to domestic installations. We're going to create a minimum viable product, so that's going to seamlessly integrate all of the steps that I talked about into one user interface, then actually verify that minimum viable product. So with that, we'll be working with exterior partners to say, okay, this is the outcome of what our rapid mapping tool assessed. How does this compare to the actual mini grid that was installed there? So for instance, PowerGen has been the developer of several microgrids, so they would be able to share with us the financial information of those projects, and we can compare how well our rapid mapping tool is doing. Then, of course, we want to protect that intellectual property, and then finally look to commercializing the entire software package. Okay, I'm gonna stop and take a quick drink of water. So switching over then, the second project that I'm going to be talking about is our turnkey infrastructure for disaster relief. This was really exciting for our team. It was actually completed last November. Yeah, I'll go ahead and hop in. So the challenge that we're trying to address here is there's over 2 billion people in remote villages and peri-urban areas, an additional 65 million people displaced due to natural disaster, armed conflict, that lack access to electricity, water, and healthcare. So what we developed is a prototype solution to create a turnkey unit that incorporates power, water, and healthcare into a modular, containerized solution capable of functioning in harsh environments off-grid. So although there are existing containerized healthcare units, what was unique about the system that we designed and built is that it also included water within the water purification within the constraints of the 40-foot container. So the project motivation here, the project was actually funded by the Office of Naval Research. So the Navy is oftentimes a first responder to natural disasters, in which case there's oftentimes not power in these locations or water, and healthcare is needed to be provided. So it would be great if they had these containerized systems on their ships to be able to rapidly deploy and provide these needs where these disasters are happening. So other than military operations and disaster response, humanitarian crises are also a great location for these containerized medical systems, and that's where we chose to deploy our system. So through partners of ours, we were able to identify that Ilo 2, a refugee settlement in northern Uganda, was the best location for us to deploy the final container in. So Ilo 2 is nearly on the border to South Sudan. It has 18,000 plus refugees at the location, and is served by a healthcare center, which is run by Medical Teams International. So Medical Teams International runs all the healthcare centers in the Ajamani district under UNHCR. And they were able to identify with us that ILO 2 specifically needed additional infrastructure. And I'll go ahead and go to the next slide here. So they, existing before the container, had 500 watts of solar PV. That's what you see on the roof there on the right. 3 kilowatt hours of degraded battery storage. So this really wasn't meeting the needs, or was not adequate power for, they see over 100 patients a day. They also have staff that live on this location. So the staff also use the power provided at the clinic. The top ailments are malaria, upper and lower respiratory infections, and skin infections. And they also support outpatient prenatal needs and so on. Another issue for this location was actually the physical space to meet the patient demand. So there's no pictures of it that I've put on here, but they actually have several temporary shelters, basically tents erected to meet their patient demand. So having that extra space was really important specifically to this location. So once we did that initial site assessment, we were able to define what the requirements were for the container that we were designing. So first, it is having stored and stable off-grid power to power the lighting, medical equipment, water processes, and so on. And this led to us designing a system with 10 kilowatts of solar PV and 60 kilowatt hours of battery storage. Now this was over-designed past the needed capacity of the clinic. That was specifically done for expansion opportunities. And actually once we commissioned the clinic on the ground, since we had the extra power and the ability to do it, we hooked up the container power system to the maternity ward and main clinic building, as well as the staff housing. So that was really great. And even at that point, I think we're still at only about 30% of the capacity. So there's still opportunities of expansion. The next requirement was ability to rapidly neutralize waterborne bacteria without chemicals or boiling. So before the container, the only potable water available was done through boiling. What we were able to provide is a UV filtration system and a water storage tank within the container that could be easily accessible through a tap outside of the container. And I'll have some pictures coming up to show that. And then finally, and possibly most importantly, is have that medical clinic space. So provide a rugged, lockable, easily sanitized space for basic medical work and equipment usage. So 20 feet of the container was for the exam room, storage for medical equipment, and then the front room, which included laboratory space as well. So here's a diagram of what the finished product container actually looked like. We had the solar panels mounted on top. That was chosen for safety, and our LEAPS actually custom designed the solar racking system. We partnered with Solar Now, which is a solar PV company within Uganda. Typically, you would ship the solar equipment within the container, but we decided it would be best to work with a solar provider within Uganda. So if any maintenance needs were required, then there was somebody there in country. And that's actually what we ended up doing, is signing a 5-year warranty with Solar Now. I think there was one issue that happened. Some breaker came loose and Solar Now was there within 2 hours to fix the issue, which is really great, having that on the ground ability to fix the power system needs. I mean, of course, we can't expect clinicians to be fixing inverters and so on. Then we have our water system. So this was custom designed by Industrial Water Innovations, which is here in Arizona. And then on the medical clinic side, the architecture was done by DIRT, and Medical Teams International actually provided the medical equipment and outfitting for the clinic. So here's some pictures from the construction at ASU. I was not a part of the team at this time, but from speaking to my colleagues, this was really exciting to do, and lots of lessons learned, and fun doing the welding and so on, and getting all the architecture in there. Like I mentioned before, everything except for the power system was actually put in the container and shipped, and that was really key to the commissioning process going successfully, is actually having all those tools, because there were many tools that we could not have gotten in country at that time. So the deployment plan, we then shipped the container from Arizona to Uganda. There were several logistic delays. It took, I believe, an extra 2 months due to customs delays on the US side and on the Uganda side finally. And then there was an extra 3-week delay because it was the rainy season, and getting to a remote refugee village near the border of South Sudan, they don't have the best road systems to take a huge container and truck through there. So there was some delays there and lessons learned on how quickly you can get a container out there. But in more standard practices where you would want these health containers to be rapidly deployable, an idea would be having regional hubs. Therefore, you could airlift or also have customs agreements to more quickly get these containers to the sites where they're needed. So here's some pictures from the final commissioning. On the left, you can see the complete solar power system, battery cabinet. On the bottom right, that was when a women's group came by and visited us, and that was actually the first time we turned on the water spigot. It was a coincidence that the water spigot came right through the Industrial Water Innovations logo, but a good coincidence. That was pretty funny. And then, yeah, you can see the solar PV modules actually on top of the container. So yeah, this was, I was here for this, and this was extremely rewarding to be a part of, to meet the community members. And then here you can see some of the clinicians and ILO 2. So on the right-hand side, that was the first time we got the lights on. So everybody was taking pictures, and we were all excited about that. And on the top left there is the first patient that was seen in the clinic. And then on the bottom left was the ribbon cutting ceremony. So we had people from UNHCR come out, from the Office of the Prime Minister in Adjumani, from MTI Uganda headquarters. It was a really big event, and made us feel really good about the impact and what we're adding to this health center. So competitive comparison, as I mentioned before, one of the biggest differences from Atlas, which is what we call our clinic container, from other portable medical systems, is that we provide water purification within the container. The other is that there's solar PV within the container. So typical designs would include a generator or connection to a grid. We could have added a generator to our system that was shipped to Uganda, however, decided not to, just based on the requirements within ILO 2. The supply lines to get diesel out there aren't really that great. Actually, during the time that we were there, in the main town of Adjumani, which is fairly sizable and connected to the national grid, I think the NGO officials we spoke of said that there hadn't been diesel at the gas station for several days. So that was just not something necessary for us to add, and we felt PV and battery provided better and more reliable power there. So some lessons learned: I already mentioned the logistics and the importance of the solar PV system warranty. We also learned some things about our water system. So actually, when we did our initial site assessment, it was during the rainy season, and the water which the health center uses comes from a rainwater catchment tank, which means it was a lot more clear in comparison to the borehole water that they use in the dry season. So actually, when they switched over to the dry season, maybe a month and a half after the container was commissioned, there were some issues with the water system. This was fixed once we realized the issue, that there was extra sediment in the water. It just meant that the system had to be flushed out and cleaned more often than usual because it's a UV filtration system. However, it's fully functioning and running. I mentioned the exterior hookups and including all tools, and then also another thing we learned is the importance of patient waiting shade. So there's long lines for patients waiting to be seen. So in future models, it might be good to include some patient shade, such as tents or something similar inside. All right, and with that, I'm gonna pass it over to Nate to talk about our energy sector workforce development.
Perfect, thanks, Elena. And so the first two projects talked about the rapid mapping, which is there's billions of dollars going into rural electrification, tens of millions of dollars a year just going into assessments, and those are relatively slow and they're not very accurate. And so if we think about the scale needed to provide power to 1.2 billion people, we need to be faster and better as engineers, policymakers, and financiers to get to that, to reach that scale. And then there was an example of how to do rapid deployment from the bottom-up perspective in a refugee camp, and then try to ask those questions, as Elena was saying, is that if you're in a refugee settlement for 5, 10, or even as much as 30 years, as we've been observing, how do you, transition or create an environment or ecosystem that supports life, but then economic development? Because it is surely not just a temporary situation you find yourself in. So again, thinking about how do we increase impact on a larger scale is we need more people doing the types of work that everyone on the phone call is already doing. And so we've been fortunate to have some federal, international financing and private sector financing to build training services that focus on the new energy economy. Next slide, please. We started this about 4 years ago, volunteering for what we call the microgrid boot camp. And so this is military service veterans who were generator mechanics, electricians, mates, aircraft mechanics, and who had skill sets that didn't easily translate into a civilian workforce after their 4, 6 year, or 20 years of service. And so we saw that as being, fairly unfortunate for those individuals, but then disadvantageous to the broader economy, and saying that we've spent a good amount of time investing in individuals to curate their skill sets, but then we just said, well, you only fit 90% of the mold, and your background in generators doesn't pertain to industrial scale power systems, so that's too bad. And so then we provided non-credit bearing opportunities to gain that additional experience with design, hands-on opportunities to allow people to get better jobs at Siemens, electric utilities, General Electric, you name it, and in this new industry. And so after about 2 years of doing this on a volunteer basis, the demand signal that we were seeing far exceeded our capacity to deliver. And so Elena, if you go to the next slide, is we started to think about, okay, how do we change the type of training that we provide and operationalize it to move ourselves from volunteers into a space where it actually has funding behind it. And so we've gotten about 1.4 or $1.5 million in training in the last 2 years to develop more programs and deliver more programs that focus on managers, engineers, operators, and technicians, noting that those are 4 technical specialities or manager style specialities that are needed for this new energy economy. And as you see there, the colors and the mapping of how those relate to the topics, it's over 100 hours, and we have about another 200 hours of content that's already developed outside of microgrid training in areas such as cybersecurity, renewables, and other systems. And so that's what we've been expanding over this last year. And if you go to the next slide, Elena, a couple of examples. We have these master classes, which are 3 to 5 day sessions, and those include continuing education credits. So for working professionals to get the credentialing, need to maintain their professional engineering exam. Those map to credentialing services in different international markets, depending on what's needed for the training services there. And so there's all of these. And then going to the next slide, Elena. An example, this was actually a while ago, I want to say this was almost 4 years ago, is the ESMAP group of the World Bank asked us to come out and do 2 days of training for them just off of DuPont Circle where IFC's at. I think it's DuPont Circle, or it could be another circle. But hands-on training and then engineering design in their facilities for country level managers that typically manage for microgrids anywhere between $20 million to $100 million per year. And they hadn't seen a microgrid before. Now they're expected to evaluate those bids that are coming in. So this was essentially an executive level training to give them the skill sets to ask the right questions on whether or not you give out tenders for people to build these things. And so there was a combination of basics, some high level information that also involved not only questions of engineering safety and finances, but then also questions of procurement and ethics. Next slide, please. I have 10 credits at ASU that myself and my team put together and teach regularly. Next slide, please. Credentialing, I already mentioned that there's credit bearing opportunities. There's continuing education credits, which are in fairly hot demand now. And it's not just through online education, but through our in-person or our online but live sessions. We give continuing education credits, 1 credit per 10 hours. And then there's a mapping of now, since we're training a variety of people, how do you create credentials that are mapped to academic needs, professional credentialing, and then defense credentialing to maintain your abilities. And that's intended to take 1 training, get 3 credentials to increase the benefit. Next slide. Even though this next year we're shooting at about 500 people being trained in the existing workforce, that's still nowhere close to what we need to meet the demand signal. And so we just right now started our pilot this week for the first 20 hours of self-paced training content. We also have semi-guided training. So every other week over this 8-week program, we have semi-guided discussion sessions with myself and other people in the team and people out in the industry in these fields that engage and talk with the cohorts of 20 individuals each about how the session is going, what are they learning, etc. And we're doing some human subjects research to compare if everyone's taking the content over an 8-week time frame. One group gets this online self-paced training, and yes, it's interactive and you have learning objects and you can build microgrids kind of like SimCity and you can simulate and see how the voltage is different. That's still pretty interactive, but you have no direct real-time human component. So how does that compare to the exact same material, but every week we get together for 90 minutes or every other week we get together for 90 minutes to chat and have a conversation about your career and where you're going in your career. And at the end, we're going to compare the results in terms of what they learned technically, how they advanced professionally, and then hopefully that'll provide us some insights for the value of that additional in-person real-time conversation. Next slide, please. We've been fortunate just this last year to do some K-12 education. That right there is a microgrid on a desk you see on the lower left, and so it combines solar, wind, storage, little small generators, and then we built these essentially small DC to DC converters or transformers that step up and down the voltage. And so if you're familiar with electric power system on a distribution network, you might be dealing with 12 kV, 25 kV, 33 kV, 69 kV, and then higher voltages. We essentially dropped the K from that, and so now it's volts. And so when people are building the little, you see on the lower right, the little high voltage power stations and stuff, they're actually stepping up and stepping down between 15, 25, 33, and 69 volts, which is safe to use. And so it's actual voltage measurements people measure and use with a multimeter, and then that game in the middle is on a tablet and they poke through on how do you build and create things, and so it gives people a hands-on way to learn and explore. Next slide. That's it. So excellent.